When I first moved to Utah a decade ago, I was working as a field geologist and was sent out to a lonely corner of Utah. On the way to the survey area, I passed into a remote region of Utah called Pigeon Basin. In this basin, I cast my eyes on a unique set of dark grayish mudstones and siltstones near the road. These rocks piqued my interest as they appear to represent a set of rocks deposited during the Dark Epoch, the Paleocene. I've been infatuated with the Paleocene epoch for nearly 20 years and have spent many years studying fossil mammals from the Paleocene in the neighboring states of Colorado and Wyoming, even writing my doctoral thesis on the Paleocene-Eocene mammals to earn my PhD at the University of Colorado. When I first moved to Utah, I wanted to find Paleocene-aged rocks, but I quickly learned that the Paleocene is not well represented in Utah. There are a few fossil sites in the early Paleocene North Horn Formation of central Utah, but Paleocene rocks are much rarer than in Wyoming, Colorado, and New Mexico. The Paleocene epoch is the least well known of the Cenozoic epochs, a time period thrown into darkness by the shadow of the great mass extinction that wiped off the dinosaurs 66 million years ago. The Paleocene ended with a great climatic cataclysm 55.5 million years ago, with a massive global warming event called the Paleocene-Eocene thermal maximum. This narrow 9.5 million year span is the Dark Epoch of the Paleocene, a world representing an Earth that was recovering from the devastation of a massive impact from an asteroid that wiped off the dinosaurs, and the initial radiation of the placental mammals. Terrestrial deposited rock layers from the Paleocene epoch contain very few vertebrate fossils. That's because most animals that were alive at the time were the size of hamsters, tiny. Although by the end of the Paleocene, some mammals reached the size of large modern bears. While plant fossils are more common in the Paleocene, fossil mammals that I study are very rare. Now, what makes me suspect that this exposure of rocks is Paleocene in age has to do with some of my experiences of studying the Paleocene and Eocene rocks in the neighboring states of Colorado and Wyoming. The Paleocene epoch, while representing a warm tropical environment in the American West, was a rich source of hydrocarbons in the form of coal and dark carbon-rich shales and mudstones. The environment likely represented a kind of swampy, poorly drained depositional environment with an ecosystem of lush semi-tropical rainforests, kind of similar to the environment of the late Cretaceous that preceded it. Now, this rich source of plants over long periods of burial and pressure turned the sediments into dark grayish rocks with inner beds of coal. However, the Eocene epoch was a much drier climate and resulted in brighter red and white bands of siltstones and mudstones. Now, this color difference in the rocks can be useful in locating the Paleocene-Eocene boundary in the American West, as there's a significant coal gap during the early Eocene as a result, resulting in these reddish rocks. And these reddish rocks was the result of course, the global warming event that in fact dried out the American West at the conclusion of the Paleocene. Now, to prove that these rocks are indeed Paleocene, as I suspect, I need to find some Paleocene fossils. And on a second trip to this outcrop, I found this. Now, in here, I found a few fossils, one of which was an edentulous jaw, which is a fragment of a dentary bone. And I couldn't identify it because it doesn't have any teeth preserved in it, but which likely was a small mammal, one of the survivors of the great mass extinction of the dinosaurs. And I also found a lot of nondescript fossil turtle shell fragments as well. Unfortunately, I've been pondering a lot of these fossils, and I speculate that these might be Paleocene in age, but they're not enough to go on. So I need to find more fossils to indicate whether or not this unit is actually Paleocene. Now, I've visited this site about 3 or 4 times, and I haven't found any new fossils every time I visit. I usually walk home without any localities. So I'm hoping today that I can prove that these rocks are indeed Paleocene in age, and they're not Cretaceous and not Eocene in age. So we'll see if we can find anything today. From this high point up here on top of the formation, the rock outcrop, you can actually look across here and see those red beds of the Eocene. So over there you can tell they're kind of reddish in color, indicating that it's that those are Eocene. And then back over here we have a ridge, this big ridge on this side, and that ridge is formed by the Erickson sandstone, which is late Cretaceous in age. So we're between the Eocene and the late Cretaceous over there. So I'm hoping that these units prove to be Paleocene. This is kind of a darker rock. It's a little bit more rich in carbon, so it's what we call lignite. Sometimes you can get these much thicker and they'll form coal beds. Though I'm not seeing any coal beds in these outcrops, but that's a nice, these are also called carbonaceous shales. They just don't have enough plant material that was turned into coal. So just probably a boggy environment. A lot of plants got buried, but not enough to form a thick coal seam. Up in Wyoming, they have some big mines in the Fort Union Formation that are pretty thick, and that they mine them in the Paleocene. You don't get this type of sedimentation in the Eocene. It tends to be red beds, brightly colored red beds, in fact. And this looks like a root cast right there. So plants for sure were here. Very ancient forest that existed here. And there were probably animals, little mammals running around, scurrying around in this forest. But I can't find them. Where are you, little mammals? Survivors of the Great Extinction. Where are your little bones? I want to find your bones! Now this rock unit is mapped on the geological maps as the Fort Union Formation. However, I'm calling it in this video the Hiawatha Formation. And if you do a Google search, a detailed Google search on the Paleocene Hiawatha Formation, you're not going to find very much. There's only a handful of papers on this rock layer. Now, to understand the Paleocene epoch, you have to go back to 1862 when geologists were first mapping Paleocene-aged rocks near the town of Williston, North Dakota, near the confluence of the Missouri and Yellowstone rivers. At the time, America's first multimillionaire, John Jacob Astor, had built a fortune trading with various Indian tribes for furs and exporting them to Europe to make fancy hats. He established a large trading post and fort along the river, and he called it Fort Union. Later, he ended up selling his interests in the business, and he invested in New York City real estate in Manhattan. Now, during and after the Civil War, the American Fur Company fort became the base for operations of the United States military. And geologists mapping the area actually used the name Fort Union to describe rock layers of Paleocene age in North Dakota. However, as more of the American West was explored and mapped, the term Fort Union was applied to coal-rich Paleocene rocks throughout the American West, including here in Utah, 800 miles or 1,200 kilometers to the southwest. Now, more recently, geologists have begun to establish more localized geological names for Paleocene rock layers. And the name Hiawatha Formation was proposed by W.T. Nightingale, who published a petroleum paper attributing the Fort Union Formation of Utah to this new local term in 1930. However, even today, on all the geological maps, you often still see the old term Fort Union used to name and map these rock units. Now, the age of the Hiawatha Formation is subject to some debate. Across the border in Colorado, fossil mammals in the 1950s from the unit indicate that the formation is actually earliest Eocene, belonging to the lower member of the Knight Formation or Wasatch Formation of the early Eocene. And these fossils were actually identified and described by Dr. Malcolm McKenna, the longtime curator of fossil mammals at the American Museum of Natural History in New York City. What struck me, however, when I encountered these rock layers here in Utah, is that they just look like they should belong into the Paleocene. And since then, I've been hoping to find fossils to prove whether this hypothesis is right, whether these units are Paleocene or not. And I need to find clearly identifiable fossils to indicate that it's Paleocene. But, I might find something that contradicts my hypothesis. For example, these might be actually still in the late Cretaceous and equivalent to the Williams Fork Formation, which they kind of look like a little bit. So if I find a dinosaur tooth or a dinosaur bone, that would seem to indicate that these rock layers are actually late Cretaceous. If I found some rodent incisors or teeth, that would indicate that they're actually indeed Eocene, because rodents really don't come in until the very, very tip of the Paleocene, but they become very common in the Eocene. Also, early horses like Eohippus appear. Many of the euprimates appear, like Cantius and Titonius would be early Eocene fossils that you'd typically see. So what I'm hoping to find is some Paleocene fossils, but we might find something totally different. We might actually find a dinosaur, or we might find an early horse. So we'll see. We're going to keep looking and see if we can find anything. When I was a graduate student, my advisor was Dr. Jalen Eberly, who is an expert on Paleocene mammals, and she took us on a field trip once to one of her localities, and a bunch of various vertebrate paleontologists. And one of the people that were on the field trip was Ken Rose, who's an expert in fossil mammals, particularly from the Eocene of the Bighorn Basin up in Wyoming. And we drove out to this one site that was a Paleocene site, and we got out and everybody was looking for fossils, and she said, "This is a really important, amazing Paleocene locality." So everybody got there, everybody's looking around for fossils, everybody's crouched down. We're there for about half an hour, no one's found anything. So everybody's just wandering around, looking, crawling the outcrop. And Ken Rose pops up and he says, "Wait, I thought you said this is an amazing locality. No one's found anything yet." And she said, "Yes, it is." And he said, "But wait, how much stuff? What have people found out of here?" And she said, "Well, in 1977, someone found a jaw of a mammal, of a Paleocene mammal." And he said, "And has anyone found anything since 1977? And she said, "No, that's what makes this such a great locality. We all came out here and hopefully maybe we'll find another jaw." So the Paleocene is fairly rare that you find stuff in the Paleocene, especially when compared to the Eocene, where fossils are much more common. So this contact right here between the sandstone up here and this mudstone here is where a river channel cut down into these sediments. And this is actually a great place to look for fossils, is what we call the lag deposits. They're at the very base of this channel. And you can see they're fairly coarse-grained at the bottom of these channels here. And these are good places to look for fossils, especially dinosaurs or bigger fossils, because if they were deposited and transported by the river and buried, you might find them down where the bigger and deeper sediments were deposited into this cut bank. And I've actually found fossil mammals in this as well. Usually they're not really greatly preserved because they've been tumbled quite a bit. You find better fossils in the mudstones themselves, or the flood, or the kind of overbank flood deposits, or paleosoils even, than you do in these. But if this is late Cretaceous, we might see a big dinosaur bone sticking out of these things. So they're worth looking at. And it's actually a really cool sharp contact here where this river cut into this mudstone that represents our overbank floodplains or deposits. Well, here's a little bit of a fossil. This is a trace fossil, probably a burrow or a root trace found in a sandstone, a cast that was made. But unfortunately, this is not telling us whether we're in the Paleocene or Cretaceous or Eocene, these rocks here. So you might be able to see that these beds are dipping in this direction here. The mountains are to our south, and so all of these beds are dipping at about a 30-degree angle. So younger is going to be to our north, and to our south are going to be the older rocks. So one of the things that keeps me coming back here is a story that was told to me by Don Lofgren, who's a paleontologist in California. And he kept going to a rock outcropping that was Paleocene in California. And he knew that he could, if he just spent enough time on the outcrop looking, that he would eventually find some fossils. And he did, after, gosh, many years of continually revisiting the outcrop that oftentimes he went home empty-handed. He would keep revisiting, and eventually he found some really nice jaws of Plesiadapis, which was a Paleocene primate, probably one of the more common Paleocene mammals that you find in the American West in the Paleocene. And it was a new species that he described. So, you know, that story keeps me coming out here, and the fact that I have found in the past some fragments, even though they're bits and pieces of turtle shell, a little bit of an edentulous jaw, keeps me coming out here because I hope to eventually find something in this unit that would indicate that it's Paleocene, like a Plesiadapid jaw, something that's recognizable. So this is one of those wonderful channels, fluvial channels that have cut down. So the sandstone here is cutting down into this mudstone, these overbank deposits. And what's really neat about this one is that actually most of these that I'm seeing are pretty small. So it peters out over there and it peters out right there. So it just kind of ends on either side. And based on the cross bedding that you see at the base here, right at this point here, some wonderful cross bedding indicates that this was flowing sort of north-south in direction, cutting down through here. And these lag deposits are great places to look for big bones. If this is Mesozoic, if this is Cretaceous, I'd expect to see some big bones or big bits and pieces of dinosaur bones maybe down in here. Not seeing that. It's coarsening upwards. So these beds down here are very coarse grained, and as you move up, they get finer grained at the top. And so these rivers would cut down into the mudstone and start to deposit on them, and then they would move across the landscape. Oftentimes you can get them stacked on top of each other with various cross beds. In fact, you got some really great cross beds here and here. So nice little channel sandstone, ribbon sandstone. So down kind of low in the valley where would be the oldest rocks, there's this interesting red sandstone that's down here. It's very different than the sandstones we're seeing up section. And this sandstone actually reminds me of some of the Cretaceous sandstones that you get in the Mesa Verde group. So I'm wondering if this sandstone, which is kind of low, might be near or contact with the Cretaceous. Wish we had some fossils to prove this, but that's kind of my idea, maybe. I want to thank my Patreon supporters, Justin Bovey and his son, Pablo Losatu Figuez, and Dan Chapshaw. You guys rock, because I was actually able to purchase a new drone also with the help of several other contributors as well. I also want to thank Dwight Howell, a longtime viewer and supporter. Thanks. I want to also thank the Forney Family Foundation, the Utah Fieldhouse Museum in Vernal, and the United States Bureau of Land Management. This is conducted under research permit UT 12-001S. If you'd like to learn more, be sure to subscribe to my channel. I also teach geology and paleontology classes at Utah State University. And if you'd like to learn about earning a degree in geology or a career in geology, check out the link below and feel free to email me.